David is a respiratory physician, as I mentioned, in Vermont, and has a great deal of experience in all things related to lung physiology and lung measurement. Has been on multiple papers that I suppose kind of set the guidelines for use of these technologies for clinical measurement. And in particular, Dave is interested in oscillometry, which he's going to talk about today, which I know many people in the Bioream network are also interested about. I think many of us are looking forward to hearing a bit more about this. Yeah, David has done lots of work related to home oscillometry in particular, which is what he's going to talk about. And yeah, without further ado, I'll hand over to David. Thank you.
Thank you very much, Carl. I really appreciate the honor of presenting today. And Bindi, I want to thank you in particular for inviting me. It's a real pleasure to be here. I was asked to talk about a study that I presented briefly this summer about measuring home oscillometry in patients who heat their homes with wood. Here in Vermont, that's quite common in the wintertime. But that's a very preliminary study, and I will show you some data from it. But instead, I thought I would focus on home oscillometry in general and provide a little bit of background about where we might be going with this very exciting technology. I wasn't sure how many people would be familiar with oscillometry, so I'd like to start by just reviewing the methodology. Here is a nice diagram where you can see a person breathing on a mouthpiece on the left-hand side, and a signal is being put into the airway via a loudspeaker that's generating a certain amplitude and frequency of pressure. And pressure and flow at the mouth are being recorded and undergo Fourier analysis to sort out the in and out of phase signals of pressure and flow. And we analyze the data to get the resistance and reactance of the system, the so-called impedance of the respiratory system, made up of these two components. And if you look at data on the right that are derived from patients with asthma, you can see how the resistance and reactance changes with severity of disease. And the upper right is resistance of the respiratory system. The flat curve with squares is the normal patient. And as the asthma becomes more severe, you see the resistance rises on the y-axis moving upward. And in addition, at the lower frequencies, it rises more rapidly than it does at the higher frequencies, so-called frequency dependence of resistance. And this is thought to relate to the heterogeneity that develops within the airway tree during the increase in resistance overall. Down below, you see reactance, and you get sort of a mirror image almost of the resistance curves in a sense. The patient who is normal or the normal control sits closest to the zero y-axis. And then as the disease develops and becomes more severe, you get more frequency dependence of the reactance as well as the curve shifts down and to the right. And this represents also the heterogeneity of the airway tree, as well as time constants throughout the lung, including the parenchymal tissues, and overall gives a sense of the so-called stiffness of the respiratory system. So it's a lot more complicated than that, and there's a lot more information to be derived, but I just wanted to make sure the basic terms were out there. The term oscillometry comes from a meeting that we had many years ago, and realized if we use the original phrase forced oscillation technique, this might turn some people off, especially patients, because it sounds like we're forcing them to do something. And we're really not forcing them to do anything other than breathe quietly on the mouthpiece. The signal is superimposed on the breathing frequency, but the term kind of had some potential negative connotations, and so oscillometry was suggested, and it's sort of in line with the term spirometry. Now, this next slide is really fun. This comes from a colleague who sent me these data before they were published, and now they've been published. It's an N of 1. It's one person who had access to a home spirometer and a home oscillometer before and after he got COVID. And on the top, you can see the FEV1 and FVC in the gray and black, respectively. And on the bottom is the diffusing capacity. And on the very left-hand side, before symptom onset, were baseline values. And then COVID occurred sometime toward the end of October. And you can see what happened to his spirometry and his diffusing capacity. His FEV1 dipped below the lower limit of normal, and he slowly recovered. His diffusing capacity dipped below the lower limit of normal and slowly recovered. You can see corresponding CT images down below that are dated showing that he has some baseline paraseptal emphysema, but there was some reticular infiltrate, especially in the periphery of the left upper, left lower, and right lower lobes that developed during COVID illness and slowly got better with time. Now, on the next slide, you can see his oscillometry results. On the top is resistance at 5 hertz, and on the bottom is reactance at 5 hertz. And you can see that the resistance rose above baseline after the onset of illness and then slowly dropped down back to actually below his baseline. And the reactance markedly became more negative, which represents markedly more heterogeneity and functional stiffness to his respiratory system that occurred immediately following the COVID illness and slowly recovered back towards baseline again. So with these kind of data in hand, we really are allowed a snapshot into real-time monitoring that we can't get when we bring patients into the clinic or the research lab, that I think really open up the future for lots of interesting research. So recently in the Lancet Respiratory Medicine, there was an article about home monitoring in interstitial lung disease, and they described this nice map of concepts on how we might use home monitoring. Starting on the left, in the pre-diagnosis period, we could start following people who are at risk, let's say, of disease and see when things might change. And then as we move rightward, we can see that we can start to monitor them more closely when symptoms develop, perhaps even try to predict when exacerbations of disease develop, monitor the response to therapy, both pharmacologic and non-pharmacologic therapy, and in patients with end-stage disease, continue to monitor them, at least by symptoms at home, so that we are keeping a close eye on how they're doing and managing their symptoms well in order to maintain quality of life and comfort. So I thought this was a nice paradigm for how we might think about home monitoring in general. Now, these are data from one study that was done with pirfenidone in interstitial lung disease, showing the clinic measurements in the dark black circles and the home monitoring of spirometry in the light gray circles. And these are 12 different patients who are participating in this particular study. And you can see there's quite a bit of variability in terms of the correlation between the so-called gold standard in clinic spirometry and the at-home spirometry. In some patients, there was nice correlation between those values. In others, there was quite an offset. For example, lower left-hand side, you can see that the clinic values were substantially higher than the at-home values. And there was a lot more variability, it seemed, in the at-home values. So there's still some room to improve this technology and the way in which we implement this, but it certainly suggests a lot of promise. And I just want to share with you another study recently published in Chest that looked this time not in interstitial lung disease, but in asthma. And you can see in the top left and right, 2 different studies that employed home spirometry. And you can see how the clinic spirometry definitely was higher than the average home spirometry values. And down below, the Bland-Altman plots show that while the overall bias was near 0, there was quite a bit of variability. And so there's more inconsistency in these home spirometry measurements. So once again, a lot of promise, but still we need to learn more about how to do this well. So I want to shift gears a little bit and go back to some old data regarding sort of real-time management of lung function. And in this case, we're just looking at peak expiratory flow. And these are data that were published showing down below in the open circles a patient with asthma who had so-called brittle asthma, someone with poorly controlled asthma. And you can see there's quite a bit of variability across a week as the peak flow measurements rise and fall day by day. Once the patient was treated for their asthma, you can see how the variability markedly reduced, as shown by the black circles up above. First of all, the circles are higher, indicating higher peak flow, so better lung function. But more important, perhaps, is the reduced variability at this stage, suggesting better control of disease. So this idea of variability is very important in helping us understand the physiological basis of suboptimal control of disease. Peter Macklem and his group many years ago up in Montreal showed that if you record impedance in a healthy subject over 15 minutes up above, you see a small bit of variability in the impedance measurement across those 15 minutes. And then if you record such impedance in an asthmatic patient, you see a slightly higher baseline value, as might be expected, and more variability across time. And in fact, you could quantitate both the mean and the standard deviation as a measure of variability and show that patients with asthma had higher variability than patients who were healthy. What was really interesting and fun in this study is they took healthy people before and after methacholine. If you look at the top row of data, upright before methacholine, and then supine before methacholine, you can see that the supine values, again, in healthy people, were slightly more noisy than the upright values, even though the mean was roughly around the same, maybe a slightly bit higher in terms of the impedance. But after you gave methacholine, lower left, you see that the upright values rose and were noisier. And then when the patient lay down, they were markedly more noisy. In fact, they looked just like the patient with asthma. And this started to give investigators a lot of insight into not only the variability, but also the importance of volume in terms of airway parenchymal interdependence and other factors that are controlling airway tone and airway diameter. This variability has subsequently been seen in many other studies. This is a study of children with asthma. On the left, you see the standard deviation of the respiratory system resistance in patients with intermittent asthma versus those with persistent asthma. And you can see the kids with persistent asthma had higher variability. And on the right-hand side was compared those with partly controlled versus uncontrolled asthma. And once again, you can see the variability was higher among those with uncontrolled asthma. Now, this study looked at the coefficient of variation of respiratory resistance during inspiration among patients with asthma or control participants over time. There's 10 asthmatics and 10 controls were studied with home oscillation done twice a day, 2 minutes at a time for 6 months. And they were able to discern that after 4 days, there was enough data about variability that they could sort out who had asthma versus who did not. And then applying this data, they were able to show that if the coefficient of variation rose above about 0.4 after only just 1 week of data, they could indicate with a probability near 100% that this is the person who is going to go on to have an exacerbation. So there was something about picking up instability in this signal prior to the actual clinical exacerbation occurring that was very valuable and might be put to use. Now, this concept has been applied to peak flow data. Erzfrei and Belasuki published a nice paper in Lancet in 2008 that kind of summarized this concept, which is looking at fluctuation analysis of peak flow over time. And what they were talking about is that these fluctuations, if you look over time, are not actually purely random, but they have similar statistical properties over different time scales, which they felt reflected their sort of fractal nature. In other words, there are long-range correlations over time, whether you look at a small time scale, minutes to hours versus days to weeks. And you can take advantage of this by modeling this behavior through a so-called fluctuation function that would be related to time and is a power law related to an exponent alpha that characterizes this long-range correlation over time, that talks about the self-similarity of the data over different time scales. Cindy Thameron applied this concept in a study published back in 2011, looking at mild to moderate versus severe asthmatics, looking at peak flow variability over time, measured twice daily, and was able to show that the patients with severe asthma had a lower alpha value, in this case 0.62, compared to the patients who had mild to moderate asthma who had a higher alpha value. Now, again, the alpha value reflects the consistency of long-range correlation, and you can kind of see that the mild to moderate asthmatic certainly had a lot of variability over time, but the wide swings in the peak flow are less so than those in the more severe asthmatics seen down below. And this was captured in the alpha value. When she looked at whether these patients had exacerbations or not, the data were a little bit different. In this case, the mild to moderate asthmatics seemed to have a higher alpha exponent who had exacerbations compared to those who did not, whereas their variability of peak flow per se was really not much different. And those data are shown on the right-hand side of this figure. Whereas on the left-hand side, in those with more severe asthma, The ones who had at least one exacerbation had similar alpha values, but had lower percent peak flow and more variability in their peak flow. And so it turns out that both components are very important. In other words, how widely does the peak flow value itself vary over time? And then how widely, if you will, does that variability over time itself vary? That's where the alpha comes into play. And in this case, the higher alpha maybe meant that these mild to moderate asthmatics who had exacerbations had too much self-similarity. They were unable to cope with a trigger that came along, let's say. And if they happened to be caught in a period of low peak flow, they couldn't break out of it. That would be one way to try to interpret this kind of finding. I was very intrigued by this, and with my colleague Jason Bates and with colleagues at Johns Hopkins University, we took some data from a large randomized clinical trial that we were involved in that was published in the New England Journal back in 2007, and we applied this concept. So this was a trial of fluticasone versus montelukast versus fluticasone plus salmeterol in patients with mild persistent asthma. And we wanted to see whether the monotherapy with montelukast or fluticasone could perform as well or maybe even better than the dual therapy with fluticasone and salmeterol. So we had a prolonged run-in phase of up to 6 weeks, and then we had a double-blind treatment phase out to 16 weeks. And we had all the patients monitoring peak flow at home. So we took these peak flow data and we calculated the coefficient of variation of their peak flow and their alpha values based on the fluctuation analysis that I just mentioned. Here on this slide, I'm showing you the coefficient of variation of the peak flow values during the run-in period up above versus the treatment period down below. And you can see in both cases, the participants who went on to have a treatment failure during the 16 weeks of treatment had higher coefficients of variation of peak flow. In other words, their peak flow varied more widely over time. And that's described here. Now, when we looked at the alpha values, we found there was no difference during the run-in phase, but during the treatment phase, the alpha values seemed to be a little bit higher in those who had treatment failure compared to those who did not. So this is really hard for me anyway. It was hard to wrap my head around in terms of trying to understand what this means. And what Jason Bates did was model these data to try to create a couple of examples that might highlight how this works. And I think this is helpful. So if you look on the left, up above, you see some peak flow data over time with an alpha value of 1. And what he's done is create two plots, one with peak flow data that has a coefficient of variation of 0.16, and another with a coefficient of variation of 0.25. And as expected, the red line, which is the higher coefficient of variation, follows the same kind of signal path, if you will, but has wider swings. It has more coefficient of variation. Down below are the data with coefficient of variation 0.16 only, but this time plotted out with an alpha value of 0.5, which is close to random. So there's random noise in this degree of coefficient of variation of peak flow. And so what we think our data means is that people who have higher alpha values, more self-similar, when this is coupled with higher coefficient of variation, such as the red curve you see up above, these people have a higher chance of having more severe persistent drops in peak flow over time. If you look at the dotted line, which represents the lower limit of normal, you can see that the red curves, for example, dip below and spend a little bit longer time below that curve than the black curve does. Meanwhile, down below, the people with lower alpha values have less self-similar peak flow. So if they happen to have a low coefficient of variation, as they do here in the black, they spend transient small amounts of time below that lower limit of 250. But if they have higher coefficients of variation, they could spend more frequent periods of time, maybe not more persistent, but more frequent periods of time below that value, and therefore have higher rates of exacerbation on that basis. So it turns out, at least by these data and Cindy Thameron's data and others, that both the variability in the parameter itself and then how that variability varies over time, both are important. So Frey and Suki went ahead and developed this very nice concept map showing how we might think about asthma in this case, or any disease really. Up above is sort of the traditional approach, thinking about a trigger causing inflammation, bronchial hyperreactivity, airway obstruction, and symptoms. But down below, we take into account the fluctuating nature of stimuli, which could be pollutants in the environment, allergens, and so forth, how this can have both short-term and long-term effects on how physiology is affected over time, and that includes lung mechanics, inflammation, and so forth. And this would translate into fluctuating symptoms over time. So perhaps we can take the fluctuating symptoms on the right, study the patterns, and work backwards to try to figure out the physiology and lung mechanics, and therefore have a way to prognosticate in terms of how our patients might do in the near future. So I like this curve. It basically sums it up by saying perhaps the signal in all of this is the noise. The noise itself is the signal. So what about COPD? This approach has been taken in COPD in a recent study published. 15 patients who had COPD did home oscillometry testing at 1 hertz, at one frequency, 5 hertz, which represents airway resistance. And they did this over 8 to 9 months. And if you look at the top curve on the left, that's their mean CAT score. The higher the score, the more symptoms they have. And down below is their, in this case, 6-day window of variability of the inspiratory reactance. And they found that this inspiratory reactance rose significantly above baseline about 3 days prior to the exacerbation occurring based on symptoms. So this might be a way to predict symptomatology in COPD patients. On the right, they compared with a receiver-operator characteristic curve how well this performed compared to the reactance itself, or the coefficient of the reactance, coefficient of variation, or the CAT score, symptom score only. And you can see it wasn't great. The area under the curve was 0.72, but it was better than the other variables. So this might be one way we can use at-home oscillometry to help predict exacerbations in asthma. I shared with you before using peak flow, and here with oscillometry in patients with COPD. There's another study that's ongoing that Rajita Rajhoshi shared with me from Cognita Labs. She's employing a home oscillation device that's portable and handheld, as you can see in the upper right, in patients with COPD over 6 months, and tracking their symptoms using the CAT score as well. So far, she's finding very good compliance with this at 85%. And here's just one piece of data showing you an example in a patient. Down below are the symptoms over time, and up above is a measure of small airway function that they are deriving from the various data they're getting from the oscillation device, and showing how the small airway obstruction is rising prior to the symptoms changing and well before the ER visit. Once again, about 3 or 4 days prior to the actual visit to the emergency department, suggesting this might be a way to not only monitor at home, but possibly predict the near future exacerbation of disease. Coming back to that Lancet medicine article that I mentioned at the very beginning, there was a very nice concept diagram here suggesting how we might integrate home measures shown in green down below that include symptoms, spirometry, I would add oscillometry, and other parameters, together with clinic or hospital measures that we might make in the pink up above. So for example, x-rays, more sophisticated lung function, blood tests, and so forth, how these might be integrated, collected into large data sets, analyzed, and individualized per patient so that we can better improve patient disease detection and management on a personalized level. So I want to shift gears now and talk about the Canadian forest fires. That's what you see on the left. Many of you may know, and Ron, you were up there yourself. There were terrible wildfires occurring across Canada this past summer, and the smoke travels around the world. It doesn't know any boundaries. And you can see on the right was the skyline of New York City in the middle of the day, where the smoke really obscured the skyline and caused this very kind of disconcerting orange sun up there in the sky. Well, we in Vermont also detected the smoke in the air. This is a map of the United States, and the different colors are different legends showing you the air quality index. Green is good, and yellow is poor, and orange is harmful. And you can see that the fires were occurring in Canada, and they were spreading south and to the east with the prevailing winds. And with the red circle is where I live in Burlington, Vermont, which is right near Montreal, Canada, in the northeast of the United States. And we were under many days of air alert up here over the summer that were quite disconcerting. And we also had very orange sunrises and sunsets too. So I bring this up because this has health consequences. This is a study that just came out in JAMA in October in New York City, where they plotted the air quality in terms of the concentration of particulates in the air on the y-axis over time on the x-axis. And you can see during one of these time periods in June, when there was a lot of fire activity, the air quality was markedly poor with a big wave of smoke that came down into the city. And they saw a huge increase, a 40% increase in emergency department visits, primarily for cardiac and respiratory ailments. So this type of outdoor air pollution affects all of us all over the planet. So what are particulates? PM 2.5, well, PM stands for particulate matter, and 2.5 stands for the diameter in microns. And you can see relative to a human hair on the left that PM 2.5 is very, very small. And why is that important? On the right-hand side, we're reminded that the size of particles that penetrates deepest into the lung are those less than 2.5 in diameter. The larger particles tend to get screened out by the mucosal membranes in the mouth and nose and eyes, and that's why allergens give us such a tough problem, because they're pretty large particles, and our eyes itch and we sneeze and so forth. But these small particles can penetrate deep into the lung, and now there's evidence that they also can carry with them various toxins, and these can be absorbed into the body, probably because of the very, very large air-blood interface that the lung provides at that level. There was a study published over 30 years ago in the New England Journal that showed that when there were more particles in the air, there were higher rates of mortality in 6 US cities. And the graph on the left shows the rate ratio on the y-axis, and the different cities symbolized by different letters shown against the fine particulate concentrations on the x-axis. And you can see that as the particulate concentration rose, so did the rate ratio, or the hazard for mortality. This really had a huge impact in terms of people understanding the consequences of air pollution. And in fact, politically, it resulted in the American Lung Association suing the Environmental Protection Agency to result in new national air quality standards that we still have today. So it was thanks to a study like this that really had some public impact. Now, here in Vermont, we don't live in a big city. We have very, very tiny cities, and many people live in homes literally that look just like this. This is a cabin in the woods in Vermont. The truck is kind of old-fashioned. As you can see, a lot of people collect these kind of things around here. But the point here is that it's wintertime and there's smoke coming out of the chimney. A lot of people here heat their homes with wood because wood is very abundant. It's felt to be a renewable resource, although there's some argument about that because, as you know, it takes trees many decades to grow back after they've been cut down. And trees sequester carbon, so we don't want to necessarily cut them down. But I don't want to go down that path. I just want to emphasize that wood burning is quite common in this part of the country, especially in the rural areas. And the reason that's important is because indoor air burning of indoor air is polluted, but so is the outdoor air. These wood smoke units or fireplaces and other types of ways of burning wood can contribute to outdoor air smoke pollution. For example, in Montana, in the United States, more than half of the particulate matter was attributed to wood smoke occurring in the wintertime. And even in the UK, a similar study was done that found that 21% of the PM 2.5 generated in the cold weather climates is attributed to wood smoke. And that was more than, that was 2.5 times greater than what cars were contributing. So indoor burning can contribute to outdoor pollution, but imagine what it does to indoor pollution. So there have been studies looking at the role of wood stoves in generating indoor air pollution. And this is just one tracing over time, showing particles of different sizes. But the PM 2.5 shown in the gray down below, over time, you can see how it's relatively low at 20 micrograms per cubic meter. It dips down a little bit lower, but then it spikes a couple of times during the day to 50 and then 100 for unclear reasons, but I'll suggest something in a moment about why that is occurring. So these particulates can definitely get into the air. And in fact, a study published out of Hopkins a few years ago looked at in-home air pollution and how it relates to the odds ratio of having exacerbations of COPD. And if you look at the graph on the left is the PM 2.5 group, and on the right is the nitrogen dioxide group. Getting back on the left, when the PM 2.5 in the bedroom, in the main living rooms, the circles was high, you can see that the odds ratio was elevated in terms of having exacerbations of disease. And the same occurred for NO2. However, in this case, it was when it was high in the bedroom area. The point of this study was just to emphasize that indoor air pollution occurs and has consequences for health. In Montana, where they study indoor air pollution related to wood stoves quite a bit, they had a program a number of years ago where they changed out old wood stoves for new ones because the new ones generate less indoor pollution. And what they were able to show here in this graph is in various homes, the PM 2.5 particles indoors went down markedly after the change out. For example, look at homes 9 and 10 on the x-axis. You can see very high concentrations above 100, and they came way down after the change out to more efficient and cleaner wood stoves. I happen to have a so-called pellet stove in our home, which burns wood pellets. Wood pellets are compressed sawdust, and they burn very, very efficiently and very cleanly, such that there's nearly no ash produced, almost no smoke you can see coming out of the chimney, and it generates a lot of heat for the home, and I'm able to save a lot of oil as a fossil fuel by burning wood instead. So these wood stoves can be very efficient and quite clean. A very recent study came out showing that applying a HEPA filter in the home can clean the air and improve the quality of life in patients with COPD. If you look above, you see the placebo group who did not get actual HEPA filtration over 6 months. And the various symbols you see are particles of PM 2.5 or PM 10 or nitrogen dioxide, and basically they didn't change over 6 months. Whereas down below in the red, the active group, you can see right away within a week, the HEPA filtration removed a lot of the concentration of these particulates and gases in the air. On the upper right is the intention to treat population. And these patients who were using the HEPA filtration did have less rescue medication use over time, and they had fewer moderate exacerbations, but they still had the same number of severe exacerbations over time. But if you stratified by adherence, if you look down below looking at a symptom score, you can see people who use their HEPA filters 80% of the time or even 100% of the time definitely had large statistical and clinically meaningful changes in their St. George Respiratory Questionnaire, which is a way to gauge symptomatology. So HEPA filtration, when used, can make a big difference in terms of health quality in these patients with COPD. There was a really interesting study from China that looked at both outdoor and indoor air pollution. And they also applied filters in the home. And in this case, on the graph on the left, they're looking at PM 2.5. And what they did is they plotted the outdoor levels in blue in 4 different homes as the nighttime went on. And you could see the outdoor levels came down by and large in homes 1 and 2, although they went up in homes 3 and 4. Indoor with a sham filtration, the indoor particles were lower, but still elevated compared to green, which was indoor with actual true HEPA filtration. And you can see in both cases, or all 4 particular cases here, the HEPA filtration was able to reduce the indoor particulates, in this case, probably coming from outdoor sources, to very low levels. On the right, they measured home spirometry and oscillometry. It's the only study I could find that used home oscillometry in this setting. And in this case, the top two rows, you can see FEV1 and FVC did not change from baseline. They couldn't detect any changes there, but they were able to detect an improvement in impedance in R5 and perhaps in R5 minus R20, which is a measure of the frequency dependence of resistance. It looks like the resonant frequency also might have come down nearly significantly. So this was a hint that oscillometry as a more sensitive test might be better able to detect these effects than spirometry. And that's what led to our local study. We had a hypothesis that it would be feasible and accurate to measure lung function at home, particularly in patients with COPD who heated their homes with wood. And we did this because there was a recent study published in this area that showed that there was a high prevalence of wood burning and there was a high prevalence of COPD, but people haven't really been able to link together in this region of the country the indoor burning of wood related to COPD. So I was hoping to try to start to get towards that by doing indoor monitoring. So our state of Vermont is very rural. It's located on the left there. The star is where the city is where I live in Burlington. And again, just to put that in perspective, that's 1 hour south of the Canadian border. We wanted to get homes that were in the rural part of the country that used wood stoves. And so we recruited patients from one of our affiliate medical centers called Central Vermont Medical Center. It's about 40 miles due southeast of us. And so my colleague and I drove down there a couple of times with our equipment. That's where we met the patients and we set them up. And what we did, shown up above, is the scheme of the study. We met them in the office on the first day. We taught them how to do the home spirometry, the home oscillometry, and how to set up their indoor air meter. Then they went home and used it for 7 days. And then they returned to the clinic on day 9, where we met them again to retrieve the equipment and complete some questionnaires. And so we used a device on the left called the Go Spiro, which is a turbine type home spirometer. And we used the same home oscillation device that I showed you previously. That's a portable device shown in use on the right. It's handheld. The participant puts a filter on, wears nose clips, and then through an iPad, both devices are able to download their data real time to the iPad, and this can also be accessed remotely, so we can keep an eye on it from our medical center here. We also had the participants fill out the COPD assessment test, the St. George Respiratory Questionnaire, and rate their level of dyspnea on an MMRC scale, and they kept a diary of symptoms as well. And this is just what it looked like in the clinic when we met them. On the left, you can see the iPad and the oscillometer. In the middle is the spirometer, and on the right, on a wood stand, is the particulate meter that we would have them place in their home, not right next to the wood stove, but somewhere in the living area that was common to most people using the home. They would plug it in, and it just runs on its own, and it collects the data remotely. And it's a very, very robust device. It can be used indoors and outdoors. It has a lot of publication data associated with it. So we felt it was a good device to use for this study. And this is just a screenshot of some of the data we got from the spirometry. You can see it's time stamped in the left-hand column by date and time. And then the spirometry values are printed out. And there's built-in quality control to look at the acceptability of the maneuvers and ultimately the repeatability. And we thought the device performed pretty well. And this is an example of the oscillometry data. Once again, time-stamped, and you can see it recorded both inspiratory and expiratory parameters, R5, X5, R20 in this case, AX, and resonant frequency. And it gave coherence values. It didn't give coefficient of variation values, but I think that's coming soon. And then we set up the device, as I mentioned, and this is just a screenshot showing at the, when I was testing this out, I tested it at home, and the number 11 is quite close to my home. Number 20 in Burlington, someone in Burlington was monitoring the indoor air. Someone up in the north near Colchester was monitoring the indoor air, and someone across the Lake Champlain in New York State was monitoring their air. And so it just shows you how this device can be used and record real time all across the country. We had 8 participants. They were on average 70 years old. They were half women and half men. One of them was still smoking. The rest had quit, but they had 46 pack years behind them. And they all had positive CAT scores indicating daily symptoms, and they were short of breath. Their FEV1s were on average at 65% of the predicted value, and their resistance values were elevated slightly at 3.5. And their AX values, normally the AX value is somewhere between, let's say, 10 and 12, and theirs were roughly double normal at 24, indicating a high area under their reactance curve. And these are data from 3 representative subjects. You see on the top row the CAT score in green, and the second row is the MMRC score in blue. The third row is the FEV1 in orange, and but down below is the PM 2.5 values that were recorded by the indoor air meter. And our sample is too small to really make any generalizations, but it was interesting to look at patterns. First of all, if you look at the PM 2.5, you can see that oscillating pattern that we saw in the data I showed you from another study. And when we talked to participants, at what time of day did they open their wood stove and refill it with wood? Sure enough, it correlated with those times. So this is one of the problems with these wood stoves. You have to physically open the door and put fresh wood in. And when you do that, the way they're designed, there can be a lot of evolution of particulates into the air at that particular moment. And some of these went up to very high values. The person on the left exceeded 600 a couple of times, which is extraordinarily high. The FEV1s kind of varied all over the place. We didn't see any clear-cut pattern in association with the PM 2.5. The patients were pretty steady in their level of dyspnea, and their CAT scores, the first 2 patients' CAT score, well, the first patient varied a little bit. The second had the same score across the entire week, and the third patient had varying levels of symptoms. Now, when we plotted these against the oscillatory parameters, we have R5 in the top row in green, X5 in blue in the second row, AX in orange in the third row. The same PM 2.5 patterns are shown below, same patients. Again, I can't say I see any patterns here. My eye wants to pretend there's a pattern in the middle patient there. The PM 2.5 goes up. The R5 seems to go up, maybe in correlation with that. Concomitantly, the X5 goes down, and concomitantly, the AX goes up. But I think that's my eye just, looking for patterns. We still need to get more data over longer periods of time to really apply a more statistical analysis to this to see if we are seeing any patterns. Of course, we're making the assumption that the time lag will be very short, but the time lag could be very long between the particles changing in concentration and the resulting lung function and symptoms. So it remains to be seen. So I think we demonstrated that we can do this. It's feasible. I can tell you the participants were very enthusiastic. We did find a few problems, though. First of all, it was hard to arrange the space and time to get these clinic visits at a rural site. And secondly, some of the patients had problems with their internet. It is a problem with rural sites, and so we couldn't download the data real time. Luckily, the devices captured it locally, and we were able to download when they came back to the clinic. So we are planning future work to explore this in more depth. And my ultimate goal is to try to establish this link between indoor air pollution and lung health in general, so that we can not only promote better education, but also public policy and try to get these, for example, these wood stove changeouts implemented here in the Northeast, where I think it's a major problem. So in summary, this is my last slide. This comes from one of the publications looking at home monitoring in 3 different ILD studies. There are a lot of challenges we still have to overcome. Patient compliance was cited in these studies. Our study was good. It only had 8 patients, but we called them frequently. We made sure they stayed on board. There are some technical challenges. I already mentioned the problem with the internet. Some other issues with data transfer occurred in some of these other studies. And then finally, how to analyze these data is still something we need to learn how to do. I think we've learned a lot from the variability studies, the fluctuation analysis that I mentioned, but we still need to obviously gain more experience with this approach. So I do have a lot of people to thank for both studies I was involved in that I mentioned to you, the fluctuation study and the wood smoke study, and my funding sources are, other sources of support are listed on the right there. And with that, I'll finish. And I do believe we have enough time for questions and discussion. Thank you so much for your attention.